Hi folks, welcome to lecture 2. The topic of this lecture is the decibel scale. So we're going to look at a little bit about where it came from, what it is, and how we use it. To kick off that expression, we'll talk about the human ear, in particular human hearing. The ear responds to sound pressure in a logarithmic fashion. And because it does this, we have a large dynamic range in our hearing capacity. And what that means is we can discern very soft or very quiet sounds that have very low sound pressure. And we can also discern very loud sounds that may have a sound pressure that's on the order of 1 or 10 million times larger than a quiet sound. So the next stop in our journey is the Bell system, which was an early pioneer in the telephone industry. And matter of fact, parts of the Bell system still exist in the form of companies like AT&T and Verizon. As you might expect, they had an interest in a way of measuring power efficiency in their transmission lines and how that would relate to what people could hear. So in the early 20th century, they developed a scale called the MSC scale, which stood for mile of standard cable. And 1 unit on the MSC scale represented the change in power level that was the smallest discernible by the average human listener. So what that would mean is if the change in power level on the line were smaller than 1 MSC, the average listener couldn't tell the difference. It had to be larger than 1 MSC for the average person to be able to tell. It was a good system, but the fatal flaw in it was that it was based on a standardized electronic test configuration. And they realized that as time went on and technology were improved, that test configuration might become obsolete. So they decided it would be good to develop a new scale that was based on a mathematical model. So in 1924, they introduced the logarithmic TU, or transmission unit scale. It had a logarithmic definition, and as you see here, 1 TU is 10 times the log base 10 of a power ratio P out over Pn. And the 1 TU is defined for the case when P out over Pn is 10 to the 1/10th power, which is approximately 1.26. In 1928, the term Bell was established, and the symbol is B, and it was developed in honor of Alexander Graham Bell. And 1 Bell was defined as the log base 10 of a power ratio, and that probably looks a little bit familiar. One transmission unit is actually 1/10 of a bell, and looking at metric measurements, we would say that's 1 decibel. So the decibel was born and is now used in many areas of science and engineering. Okay, let's look at a couple calculation examples. We'll start with the simplest case where P out and P in are the same. So that means that the ratio of P out over P in is 1. Well, the log base 10 of 1 equals 0. Therefore, 10 times the log base 10 of 1 is 10 times 0, which is 0 decibels. So that's what we have in the case when the input and output power are the same. The gain in decibels is 0 dB. The gain unitless is just P out over P in, which is 1. Now let's take another case. Let's go for 2. So P out over P in equals 2. So we'll just go directly 10 times the log base 10 of 2 equals 3.01 approximately, which is really approximately 3 dB. So if the output power is twice the input power, the unitless gain is 2, and the gain in decibels is 3 decibels. So let's jump up to something bigger. Let's say P out over P in is, say, 25. Well, 10 times the log base 10 of 25 is roughly 13.98, which we would say is approximately 14 decibels. So, right, in the case of 1, we had 0 dB. In the case of 2, we had 3 dB. But now we see, because of the logarithmic nature, when we go to 25 unitless, we've only gone up 14 dB. And let's do one more, an even bigger number. Say P out over P in is 500. Well, 10 times the log base 10 of 500 equals 26.99, which is approximately 27 dB. Okay, so now we've got up to a factor of 500, but in dB it's only 27 dB. So there we can really see what's happening with the logarithmic nature of the calculation. Okay, so now let's look at what happens when the gain is smaller than 1, right? Realize that at unity gain, or the gain of 1, we have 0 dB. But now and I'm going to put something up here just as a reminder that in the case of a gain of 2, so P out over P in equals 2. We just did this on the previous slide, so that means 10 times the log 10 of 2 equals approximately 3.01, which we said is 3 dB, really close to 3 dB. Now, what if it is the gain instead of 2 is 1/2, so we're going to have the reciprocal. So that means P out over P in equals 1/2. Well, 10 times the log base 10 of 1/2 is approximately equal to negative 3.01, or negative 3 dB. So what we see is if the unitless gain is the reciprocal from going from 2 to 1/2, then the gain in dB is going to be the same magnitude, but it's going to change sign. It's going to become the negative. Okay, so now let's look at, let's jump right to 1 over 500. So if P out over P in equals 1 over 500, then 10 times the log base 10 of 1 over 500 equals negative 26.99, or approximately negative 27 dB. Okay, so what we had before for the gain of 500, we had plus 27 dB. So that's an important thing to note. And what about, can we get to negative infinity dB? Well, the answer is no, but matter of fact, we can't even get, if the output over the input power keeps getting smaller and smaller and smaller, what we can't deal with is this. If we have P out over P in equals 0, unitless, then 10 times the log base 10 of 0 equals not defined. So we can never get there. Okay, so we do have to pay attention to what that means. We've always got to have a non-zero um, gain in the unitless gain. Obviously, we can have a 0 dB, which corresponds to unity gain. Now, we've been dealing strictly with power ratios, but mostly what we've been talking about from the circuit side of thing is voltage ratios. So how does all this fit together? Well, it turns out we know that power is proportional to the square of voltage. Okay, so and specifically we have power equals V squared over R. Now that's a basic DC calculation, but conceptually we understand what that means. But all that tells us is that power is proportional to the voltage squared. And so if we put our input and output power, if we relate them over a common resistance, where we have Pn equals some Vn squared over R, and we have an output power, P out equals V out squared over R, then we can take that ratio, and that ratio would be P out over Pn equals, and then we just carefully write these, V out squared over R divided by Vn squared over R. And we'll notice that what we end up with is V out squared over Vn squared. Now, what do we do with that? Oh, by the way, we can also write that as V out over Vn quantity squared. So now what do we do with that? Well, let's compute again using the same formula. Let's look at the ratio in decibels. So we're going to have 10 times the log base 10 of P out over Pn, and that's going to equal 10 times the log base 10 of V out over Vn, that quantity, let's put another parenthesis there, quantity squared. Now the nature of the logarithm is if we square a value, we can actually pull the square out and just multiply by 2 out in front. So that's going to turn out to be equal to 20 times the log base 10 of V out over Vn. Something to keep in mind is we also know that power is proportional to the square of current through the expression I squared R. So all of this discussion actually works with current ratios as well. So if we want again, we're looking at power ratios, but if we have power values where we have a P out over a Pn, the expression in decibels would be 10 times the log base 10 of that ratio. If we have the expression in current or voltage, basically a waveform expression, then we have to use the 20 out in front and not the 10. Okay? So to recap, what we have is for power ratios, we use 10 times the log base 10 of P out over Pn. And for voltages and current, so we'll say for signal waveforms, this would be voltage ratios or current ratios. We use 20 times the log base 10 of V out over Vn, or I out over In. So again, don't forget when to use the 20. Mostly that's what we're going to use for our signal analysis because we are talking about voltage gain ratios or possibly current gain ratios. So let's drive this point home just by looking at some voltage gains. In particular, we just want to see the conversion. So if we have unitless voltage gain, so we'll say up here unitless voltage gain. Okay, that's on this side, and over here we just want the gain in decibels. So the gain in dB. All right, so let's start with something really small, like a gain of of 0.0001. That's going to be 10 to the minus fourth. Well, by looking at this, if we compute the log base 10 of 10 to the minus fourth, we should just get a minus 4, and then we got to multiply that by 20, so we get 20 times negative 4, which is negative 80 dB. All right, so carrying on with that, if we have a gain of 0.001, which is 10 to the minus 3, then we're going to have a minus 3 times 20, which gives us minus 60 dB. And you can see the pattern here. If we have a gain of 0.01 or 1/100th, that is 10 to the minus 2. The log base 10 of that is negative 2. Multiply that by 20, we get negative 40 dB. If our gain, a unitless gain, is 0.1 or 1/10, we have 10 to the minus 1 power. Take the log base 10 of that, we get negative 1 times 20, we get negative 20 dB. Now we get to unity gain. We know that's 10 to the 0 power. The log base 10 of 10 to the 0 power is just 0, so that's going to be 0 dB. And then we start building up in positive gains. So now we can have a gain of 10, we can have a gain of 100, we can have a gain of 1,000, and a gain of 10,000. All right, so we can write out what each of those is. So one's going to be 10 to the first, which is going to be the log base 10 of 10 to the first power is just 1 times 20 gives us plus 20 dB. If we have a factor of a gain of 100 unitless, that's going to be 10 squared. So we multiply the 2 by 20, we get plus 40 dB. A factor of 1,000, we get 10 cubed. The log base 10 of 10 cubed is 3, so times 20 gives us plus 60 dB. And finally, we have our 10 to the fourth case, and that will yield plus 80, or I'm sorry, yeah, let's not scribble that out. Let's just rewrite it as plus 80 dB. So I hope this gives you a little bit of insight as to where it came from, where the decibel scale came from, why we use it, and essentially it gives us a way to compress. If we had to plot values on the range of 10 to the minus 4 all the way up to 10 to the 4 on a unitless scale, it would be virtually impossible. But it's not unheard of to be able to think of values ranging from minus 80 to plus 80 on a scale. So that's really why we want to use it. And let's make this arrow down here fit. How about that? We'll just cut it off, make it there. So we're going. So what we've done is we've essentially compressed the dynamic range by using a logarithmic scale for our values, and that's the purpose of the decibel scale. So that's all we'll do for this session. We'll dig more into frequency response and Bode plots in the next session. So thank you for listening, and I hope you have a good day.